Okay, so get this, everybody. Transformers.
Yeah.
Right. Everyone's been talking about them, how amazing they are for machine learning. And don't get me wrong, they are powerful, especially for sequence modeling.
Oh, yeah.
But
yeah, they can be
real resource hogs.
Yeah, you're right. You're hitting on a major pain point for a lot of people, especially when you're dealing with really long sequences of data. And that's where this whole idea of revisiting recurrent neural networks, RNNs, as I'm sure you know, comes in.
Right.
We're talking about potentially making things way more efficient.
Yeah, and that's where this research paper that we are diving into today comes in. I love this. They ask a really bold question. Were RNNs all we needed?
Yeah.
Now, before we get too ahead of ourselves,
right,
let's rewind a bit.
Okay.
You've probably heard of LSTMs and GRUs.
Absolutely, yeah. LSTMs, long short-term memory networks, that go way back to 97.
Wow.
Ancient history in the AI world, right?
Right.
And then you have GRUs, gated recurrent units, which came out in 2014. Both were designed to handle sequences like natural language or time series data, but they had this big limitation.
They were all about that sequential processing life.
Yeah, you could say that.
Like trying to eat a whole pizza one bite at a time.
Yeah.
When you could just conquer it slice by slice.
Perfect analogy. That sequential processing, known as backpropagating through time, or BPTT, made them slow and hard to scale, especially compared to the parallel processing power of those transformers we were talking about.
So they got benched for being too slow, even though they had potential.
Yeah, pretty much. It's sad, but that's the AI world for you.
That's where this research gets really interesting. They found a way to basically re-engineer LSTMs and GRUs, stripping them down to their bare essentials. No more BPTT bottlenecks.
What's really fascinating here is that they created these minimal versions, min-LSTM and min-GRU, and they didn't just get a little speed boost. We're talking massive efficiency gains.
Like going from dial-up internet to fiber optic speeds.
Mm-hmm. Exactly. And they achieved this in two major ways. First, they massively reduced the number of parameters these models use. Imagine taking a complex machine with 1 million knobs and dials and stripping it down to just the essentials.
Talk about decluttering. And this decluttering has a direct impact, right?
Right, absolutely. Fewer parameters translate to faster processing and less memory required. To put it into perspective, a min-GRU uses about 33% of the parameters of a standard GRU when the hidden state size is equal to the input size. And as the hidden state increases relative to the input size, the min-GRU uses even fewer parameters.
Wow.
This leaner design makes a world of difference.
So they basically Marie Kondo-ed these models. But that's not all, right? They also found a way to unlock parallel processing for these min-RNNs, which was previously thought to be impossible.
Precisely. Think of it like this. Instead of a single worker meticulously assembling a product step by step, you now have a whole team working on different parts simultaneously. This parallel processing led to some pretty astonishing speed improvements during training.
Give me the numbers. How much faster are we talking?
Hold on to your hats. For a sequence length of 512 on a T4 GTU, the min-GRU was a whopping 175 times faster than a traditional GRU. That's like compressing a year's worth of work into a single day.
That's a serious game changer. But here's the real question. Does this newfound speed come at the cost of accuracy? To find out, the researchers put these min-RNNs through a series of rigorous tests. They wanted to see how these streamlined models would perform on 3 key tasks. And trust me, you'll be surprised at what they found.
So you know how in machine learning there are always these benchmark tasks?
Right.
They really put models to the test.
Oh yeah, absolutely. It's like their AI Olympics.
Exactly. So the first challenge they threw at these min-RNNs was the selective copying task. And basically you can imagine having this giant haystack of data.
Okay.
And you need to find specific needles hidden within it.
Oh wow.
That's essentially what this task is all about.
Sounds tricky. It requires focus, memory, the ability to sift through a lot of noise.
Yeah.
Did our minimalist champions rise to the occasion?
You bet they did. What's really remarkable is that the min-GRU and min-LSTM were able to solve this task accurately, while other, more recent models, like H3 and Hyena, really struggled. They struggled to achieve the same level of performance.
Hold on, that's huge. These stripped-down models, despite their simplicity, outperform some of the hottest new architectures in a task that demands both memory and precision.
It makes you think, right?
It does.
Like maybe bigger isn't always better.
Right.
Now, get ready for round 2 of this AI Olympics.
Okay.
Because they then tested these min-RNNs in the world of reinforcement learning.
Okay, so we're talking about robots learning to navigate the world, make decisions, and accomplish goals based on experience, right?
Precisely. Specifically, they used this thing called the decision transformer framework. So they had these min-RNNs controlling simulated robots.
Good.
In a variety of tasks, think walking, hopping, balancing, all those really hard things to do.
Yeah. Like a robotic boot camp for these AI models. They survived.
Not only did they survive, they thrived. The min-LSTM and min-GRU consistently outperformed another model called Decision S4 and even achieved results comparable to some of the top performers in reinforcement learning, like Decision Transformer, ARIN, and Mamba.
So they're holding their own against the reigning champs of the AI world, even in a completely different domain. That's incredibly impressive. But wait, there's one more test, right?
Right.
The language modeling challenge.
Yep.
The ultimate test of AI's ability to understand and process human language.
It all comes down to this.
Exactly.
For this final challenge, they trained the min-LSTM and min-GRU on the works of Shakespeare.
Talk about a crash course in language. Shakespeare's got it all: complex sentence structures, double meanings, puns galore. How did these minimalist models handle the bard?
Well, they didn't write any sonnets,
Right?
but they did achieve accuracy comparable to that of transformers, which is saying something.
So even after all these years, LSTMs and GRUs, in their new minimalist forms, can still keep up with the supposed gold standard of language modeling.
Yeah, and it wasn't just about keeping up. What really stood out was the efficiency. The min-LSTM and min-GRU achieved this level of accuracy with significantly fewer training steps than the transformer.
So not only are they performing as well, but doing it in a fraction of the time. That has huge implications. Think about the amount of time and computational resources it takes to train these large language models.
Yeah.
If we can achieve similar results with fewer training steps, that's a game changer.
It means faster development cycles, reduced costs. It could even mean wider accessibility to these powerful AI tools.
Yeah.
It also raises some really interesting questions.
Like, were we too quick to dismiss these classic architectures?
Exactly. This research has certainly made the AI community take a second look at the potential of LSTMs and GRUs, especially in their streamlined forms.
It's a good reminder that innovation isn't always about inventing something entirely new. Sometimes it's about revisiting the fundamentals with fresh eyes and seeing what we might have missed the first time around.
Couldn't agree more. Now, while these results are certainly exciting, it's important to remember that this research is just one piece of a much larger puzzle.
You mean it's not as simple as saying RNNs were all we needed all along?
Exactly. While this research shows the incredible potential of min-LSTMs and min-GRUs, it's not a case of one size fits all. Every AI task has its own unique challenges, and different architectures have their own strengths and weaknesses.
So it's about choosing the right tool for the job, even if that tool is a classic that's been given a modern makeover. But this begs the question, where do these min-RNNs really shine? And where might they fall short? It's like that old saying, don't judge a book by its cover.
Right.
Or in this case, don't judge an RNN by its age.
Well said. You see, this research didn't just explore the capabilities of min-RNNs, it also highlighted some of their limitations.
Okay.
So remember those robotic tasks we talked about, like how well they were doing?
Yeah.
Well, it turns out that while the min-RNNs did really well in those simulated environments, their performance wasn't as, how should I say this, stellar, when the researchers made things a bit more tricky.
Curveballs, like making the robots walk on uneven surfaces or in changing weather conditions.
Exactly. Tasks that introduce a lot of unpredictable variation.
Right.
That's where some of those other architectures, like transformers, they still have an edge. They seem to be better equipped to handle those unexpected twists and turns.
This is not a case of min-RNNs coming in and replacing everything else.
It would be nice, right?
It would.
Make our jobs a little easier.
Exactly.
But no, they're not a magic bullet. They're a really powerful tool, but just one tool in the AI toolkit.
Okay.
And the key is understanding their strengths and weaknesses so you can choose the right tool for the job. Speaking of which, how do you think this could change things in your world?
Now, that is the million-dollar question, isn't it?
Hmm.
And it's one that hopefully all of our listeners are pondering right now as well. So think about the sequence modeling tasks that you are currently tackling, or maybe even the ones you've always dreamed of exploring but thought, it's just too computationally expensive. I don't have the resources for it.
Right.
Could min-RNNs, with their efficiency, with their surprising capabilities, could this open up new possibilities, streamline your existing workflows?
Imagine being able to prototype ideas faster, test models on larger data sets, or even deploy these sophisticated AI models on devices with much more limited computing power. These are just a few of the potential benefits that MinRNNs could bring to the table.
It's like we've unlocked this new level of, AI accessibility.
Yeah.
And efficiency. Who knows what innovative applications we'll see emerge as more people start experimenting with these minimalist designs.
That's the beauty of research like this.
It is.
It doesn't just give you answers, which sometimes it feels like we're desperately searching for in this field. It sparks new questions and inspires, hopefully, a whole new wave of exploration and discovery. And who knows, maybe this blast from the past
I love that.
will inspire you to take a fresh look at some of those quote-unquote outdated ideas in your own field.
I love it.
Yeah.
Another deep dive completed, and we've only just scratched the surface, as always. But hopefully this has been a really fascinating journey back to the future of RNNs. Thank you so much for joining us. Until next time, keep those minds curious and those algorithms running.
Here, here.